I apologize again for the sound quality on this one. I switched back to the good microphone, but I don't know what happened. It recorded with something else.
Hi class, we were analyzing a trailer hitch that's mounted by 4 bolts. This photo here is from this website. If you haven't, maybe take a look at the video that talks about how it's installed, but it mentions in the video what bolts to use, 5/8 inch SAE grade 5. That's also in the instructions here on the website for the installation details. We did an analysis of that. It says the torque from 150 foot-pounds, and we were taking a look at what the joint stiffness coefficient was going to be, and then what the tension in the bolt would be if it's pulling a load up a grade. So in order to figure out the total tension in the bolt, you need to know that joint stiffness coefficient. And in order to do that, you need to know the stiffness of the bolt and the stiffness of the member. So let's look at how to do that. So here's a diagram of our situation. We've got an 5/8 11 SAE grade 5 bolt that is going through, we'll say, a washer. It's not shown in the video, but I'm going to include one. It's a good idea to protect that fillet under the head of the bolt. Then there's the hitch itself, and that's being bolted to the trailer, and then we're going to have a nut on the far side. Both the hitch and the trailer, these are each 1/2 inch thick, and they're made of steel, and we want to figure out, first we're going to figure out what KB is. That's the stiffness of the bolt. So what is KB? This page of Shigley is your friend when you're trying to figure this sort of thing out. So it gives basically step-by-step instructions for doing that. So if you're given a fastener diameter D, let's zoom in a little bit, and a pitch P, or number of threads per inch, well, we're going to have to figure what these are. So D, that's the major diameter of the bolt, that's 5/8 inches, and the pitch P is, well, we've got 11 teeth per inch, so the pitch is 1/11, 0.091. Okay, so we have that. The next thing we need to do is figure out what the washer thickness is. What's the washer thickness that corresponds with a 5/8 inch bolt? That wasn't given as part of the problem here. We know that these are 1/2 inch, but in order to figure out the total grip length of the bolt, which is going to help us figure out the stiffness, we're going to have to figure out how thick this washer should be. So there's a table in the back of the book, dimensions of metric plane washers. We've also got dimensions of American Standard washers. This is the one we want, and so it gives typical washer sizes for different bolt sizes. We're going to look at the 5/8 inch. Let's do the normal washer, 0.095 inches, and so we can use that. Okay, so we have the washer thickness. We also are going to need to figure out the nut thickness. And the reason we have to do that, I mean, we ultimately, what we're after is how long is the grip and how long is the threaded portion of the grip relative to the unthreaded portion. So we need to take those two different segments into account to figure out the total stiffness. But in order to figure out how much of the bolt is threaded, and therefore how much is in the grip, we have to figure out how long the bolt needs to be. In order to do that, we need to make sure that it passes all the way through the nut. So we need to know the nut thickness, H. So H here, we can also look that up for a 5/8 inch bolt towards the back of the book. So here are dimensions of hexagonal nuts. We have a 5/8 inch is the nominal size, and the height, H, for a regular one, we'll just use that, is 35/64. There might be some argument for using the thicker 23/32 one, thick one, because we are going to be using a lock nut. For right now, we'll say it's 35/64. Really, you want to look at, if you were analyzing this for an actual piece of hardware, you'd want to find the nut and then that you're actually going to use and figure out what its thickness is. So 35/64 inches. And now the grip length is all of the material that is squeezed between the face of the bolt and the nut. So in this diagram, it's everything between the face of the bolt here on the left and the nut on the right. In our diagram, it's everything between here, face of the bolt, and the face of the nut. So it's the thickness of the trailer plus the hitch, that's 1 inch total, plus that of the washer. So our grip is going to be L is equal to, we've got the 1 inch from the trailer and the hitch, plus we've got the 0.095 for the washer, 1.095 inches. Now, if you had a situation where it was a screw that was threaded into something other than a bolt, threaded into a part, then you can use these equations here. It suggests that you say the thickness, the length is whatever h is, whatever all the material that you're going through. So you're going through the washer in this case, you're going through another part, and then you're threading ultimately into this part. And it says to use, in addition to the washer thickness t and the thickness of this part, the total dimension h, in addition to that, you're going to go d over 2 further. Or if this part is really thin here, if T2 is less than the diameter of the bolt, then you're going to do T2 divided by 2, half of that. The fastener length, we need to find out what the length of the fastener is. We need to make sure it is greater than the grip, L, plus H, the thickness of the nut. You need to make sure that you get all the way through the grip and plus the width of the nut. In our case, you need to go all the way through the grip and then also through the nut. It needs to be greater than that. So our L must be greater than L plus H, which is equal to 1.095 plus 35/64. That's 1.641 or 1.642. We don't need the rest of the digits because we need to be greater than that. We're going to choose a preferred size. It says round up using table A-17. Now again, if you choose the actual hardware, you should use the actual dimensions of the hardware. But here we're going to use preferred sizes that are in the back of the book. So table A17 is preferred sizes. We have greater than ½ inch, but it's less than 1 3/4. So we're going to use 1 3/4. 1.75 is what L is going to be. So 1.75, which is our L, is greater than this. It's the first preferred size that is long enough to fit through the grip and through the nut. So let's find the threaded length of an inch series bolt is what we have. If it's metric, it's a little bit different. If our bolt is less than 6 inches long, if L is less than 6 inches, which it is, then we're going to use this equation. The threaded length is 2d plus 1/4 inch. So L sub t, the threaded length, so however long the bolt has threads, is 2 times the diameter plus 1/4 inch. We've got a 5/8 inch bolt. We're going to add a 1/4 inch. So that's 10/8. That's 1.25 plus 1/4. Another 0.25, that's 1.5 inches. That is the length that's threaded. Then the length of the unthreaded portion, all of which is in the grip, right? So we're thinking about how much is unthreaded. All of that is contained in the grip because the nut is on the end. That's on the threaded portion. The entire unthreaded portion up here, the head of the bolt, is going to be going through the grip, which includes the washer and everything that's between the head of the bolt and the nut. So the unthreaded portion of the bolt, the unthreaded portion that's in the grip, LD, is L minus LT. It's the length of the bolt, the whole length, minus the threaded portion. So you could call this uppercase L. I think that what it's going at is uppercase is the convention for the total length. L is the total length of the bolt. L sub T is the total threaded length. We're going to calculate also lowercase L sub T. That's going to be the portion of the threaded part of the bolt that's in the grip. Lowercase L sub D is the portion of the unthreaded part of the bolt that's in the grip, but that's equal to the whole unthreaded portion of the bolt. Okay, so we've got 1.75 inches minus 1.5 inches. We've only got a 1/4 inch of the bolt that's unthreaded, and all of that is in the grip. Then it says calculate LT. This is the threaded portion that is inside the grip. It's going to be whatever the grip is minus the unthreaded portion. And that's 1.095 minus 0.25. That's 0.845 inches. Then it says the area of the unthreaded portion, AD. Well, it's unthreaded. The major diameter is D. That is the diameter of the unthreaded portion. So it should just be pi d squared over 4. And yeah, that's right. Pi d squared over 4. That's 0. Write it out to the bitter end, 0.3 inches squared. And then the tensile stress area is the area of the threaded portion. You look up the tensile stress area from the table. Table 8-2 has it for UNC bolts. 5/8, 11.226 is our tensile stress area. So a lot of this is collecting numbers. I think we're nearly at the end here. All right, our last step is to figure out the fastener stiffness. Let's see where this equation for fastener stiffness comes from. We can just plug and chug from here, but I want to show you where it comes from. It's just a series, 2 springs in series, basically. And we're going to take a look at the deflection of the bolt in order to get there. So the total deflection of the bolt under a load is the deflection of the threaded portion, which we'll call delta T, plus the deflection of the unthreaded portion, which we'll call delta D, where the subscripts are taken from above to mean the threaded and unthreaded portions of the bolt. So how much does this part in the grip deflect, plus how much does this part in the grip deflect? And the deflection of the threaded portion is, well, you remember PL over EA, that formula? That's the deflection of a cylinder under a load P. So if we've got load P, and this has cross-sectional area A, we need to know how long it is, and we need to know what the material's property is, the material stiffness E is. In our case, that is whatever our load is, which we don't know. We're finding this in general. For our general load, we know that L is L sub T. It's the length of the threaded portion that's within the grip, because that's the only part that's under the load and is going to elongate. E is the material stiffness of the bolt, and A sub T, that's the tensile stress area. It would make sense to use that to see how long it elongates, because that's how we calculate the stress. Makes sense that we calculate the strain using that same area. Okay, so that is the deflection of the threaded portion. We've also got the deflection of the unthreaded portion. That's PL sub D, the unthreaded portion within the grip, over EA sub D, the unthreaded area, cross-sectional area. And so delta is the total deflection. It's P times both of these things, LT over EA plus LD over EAD. But what we're really after is we want to know what is the stiffness, right? The stiffness K, the total stiffness of the bolt, is the load to cause a given deflection, delta. So what we have really is P over delta, which is P times all this stuff. So it doesn't matter what P is, that cancels out. So all that's left is to simplify, and if you do the algebra, you'll find that it is equal to what it shows here. We've got AD, AT, E over AD, LT, plus AT, LD. Okay, so that's our formula. Let's plug in the numbers. Our AD was 0.3 approximately. Our AT was 0.226. Our E is that of steel, 30 times 10 to the 6 PSI. We'll just keep our units consistent. AD again, 0.3. LT is the threaded portion that's in the grip. That was 0.845. AT was 0.226, and then we've got the unthreaded portion of the grip was 0.25. And we get 6,561,290 pounds per inch. It takes 6.5 million pounds in order to stretch the bolt 1 inch. Now it's probably going to break before that, but that's how long that's how much force it would take in order to stretch it. So that is the stiffness of our bolt.